And third assumption is the no perfect correlations. So which means if the none of the independent variables are constant and there is no exact linear relationship among the independent variables, which means if we have a clear linear previously we saw that we can have x and x square as a separate vector, the factor. But if we have something like that, so x and y, x1 and x2, but indeed x2 is just 3 times of x1. The problem is we can have a, let's say, when we learn the regression, then you can find this is like a 3x1 times 4x2. But if the x2 is a 3x1, right? So this will be the same as a 15x1, or if this is true, what we can do is a 15x1 is like 12x1 plus 1 times x2. This will be the also 15x1, right? Because this is the 3x1, so it's a 15x1. So we can create a lot of different form. So which means we can rely on these numbers. We don't know it will be 12, 1 or it will be 3 and 4. We have no idea. That's why this collinearity causes a lot of problem when we estimate what is this coefficient. It is all the same model actually. If x2 is a 3x1, this model and this model are the same model. So this assumption only rule out perfect correlation, but when in reality actually there is a little bit of a correlation. Even they doesn't have any physically or meaningly, they don't have any relationship at all, but since they are most like a random sample, so they can have a slightly correlations. So you cannot have a perfectly uncorrelated variables. So a little bit of the correlation is imperfect correlation is allowed. However, you can see there could be some bias if the correlation is significant. So we will talk about that in model selection later. So which variable should we include? Yeah, so if it's one of them is a perfect linear combination of other exponential variable, then you should get rid of them. So constant variables also ruled out because constant variable will have a correlation collinear with the intercept. Intercept is the constant value, and constant variable also should be like that. The y-intercept y equals like 15 plus 4x1 plus 2x2 plus 3 is this is like a variable, then it should be added to here, right? So that's why this is a collinear with the intercept. So this constant variable you can write this 18, or you can write this like a 12 plus plus 6, right? So we don't know which one is right. So going back to the average score in the school, expenditure per student and then average income, family income. So again, we can easily expect the school expenditure per student has a highly correlated with the average family income, right? So how can I completely separate these things? Is that that's not possible. And then this case is the relationship between regressors, perfect correlation. This is a perfect correlation case. Share A and share B. This is like a relationship between like this, right? So one goes up and then the other one goes down. It has a kind of perfect correlation, negative correlation. So this case we have to take it out, one of them. So here the small sample, yeah, you can see the very strong correlations. So it may not possible, you can separate out. If there is a lot of sample, actually you can find some uncorrelated cases. So high expenditure but the low average income case, if you have that cases in your sample, then you can separate out somehow. But in small sample, maybe you cannot have that kind of the cases. Then you cannot separate out. Zero conditional means expectation of the residual should be zero. That's a summation of all residual should be zero. Okay, and so here the average score is expenditure times average income. But if we take it out this average income, this one altogether, this will becomes U, right? In that case, why U should be the zero? I mean, the expected value of the U should be the zero, because the U should not correlate it. Actually, the correlation between the X I and the U should be zero, but because the average income is correlated with the expenditure, so it's gonna be hard to defend the expenditure. It's uncorrelated with the error term. Irrelevant variable. What if we include the factor that is totally irrelevant? Actually, that doesn't have any prediction power, but because before we run the regression, we don't know, right? So we can just put all the possible factors. Maybe we include some factor that is totally irrelevant at all. But that's fine, because you will find if this is really irrelevant, the coefficient will be zero or nearly zero. Okay. However, the including the irrelevant variable may increase the sampling variance. So we will talk about the variance, sampling variance, and the error variance later. But if you add that, your sampling variance may go up. So simply you can just take it out, irrelevant variable. So this is a true variable, but estimated variable, maybe you can take it out. This is omitting the relevant variable. So you should have this one, but you may exclude that part. And then again, we know this beta 1 and beta 0 will be biased when you're taking out the relevant variable. So biased estimator. So we can, if we can, this is similar to the partialing out. If I can do the regression for the x2 using x1, and you can do the regression, and then this is the error term. If x1 and x2 are correlated, then which means we have a positive or negative, so non-zero value here. So you can just replace x2 with this number. Then you can just expand it, and then this and this time goes to here because it has x1, and this times this will goes to here, and then this times this and add it to the error, right? So as you can see, the actually what we expect to have a beta 1 is if x1 increased by 1 unit, how much y change? That should be the beta 1. But here, if we regress do the regression with only x1, actually this beta 1 is biased, right? So as you can see, all the variable beta 0 and beta 1 and then even error term, all of the coefficient will be the bias if we take it out, the omit a variable. Overestimation. So if this is the positive, okay, so this is the real relationship. So wage is the part of the affected by the education and affected by the ability, and we have a beta 2 here. But if ability can be explained by the education with the error, then we can replace ability with this form, right? And then you can clear the formula, then we will have this one. So if this is the positive, right, then this will be positive, and then what will happen is this beta 1, new beta 1, will be overestimated because of this ability disappeared. This is what happened we omitting the ability. The real problem is we don't know what is the real population regression. That's the biggest problem. So when we omit the one factor, when you don't know, did I omit some variable that should be in there, or we don't know. So when there's no omitted variable bias, so this is the bias because of we omit the variable. So when there's no bias when we take it out, but if the variable we omit was irrelevant or uncorrelated, totally uncorrelated with the others, uncorrelated with means this will be 0, right? And this is, since this is a 0, even though beta 2 is not 0, this is 0, this will be the 0, and beta 1 remain the same. So either this is a totally irrelevant variable, or is completely uncorrelated with the other variable, then it will not be biased.